Hi, in this session, I'm going to talk about central limit theorem for proportions. The central limit theorem for proportions can be stated as follows. If we have a population in which a characteristic has a proportion p, then the sampling distribution of the proportion estimated from several samples of size n, let us say the estimated value be p hat, will follow a normal distribution with mean p and standard deviation under root p times 1 minus p over n. So, let us try to understand the sampling distribution of proportion and central limit theorem of proportion. So, we are talking about a situation where we are estimating a proportion For example, let us assume that we are estimating the proportion of people who would return the products purchased from e-commerce sites. So, the proportion that I am interested in is proportion of customers who would return products purchased by them. So, I am going to assume that in the population, the proportion of customers who would return the items purchased by them is P. But typically what we do is we collect a lot of samples. From that sample, we estimate the proportion. So, I am going to assume that the estimated proportion is P hat. In that case, the estimated proportion will follow a normal distribution. So, basically, the sampling distribution of the proportion will follow a normal distribution. With mean P, which is same as the population proportion. The standard error under root P times 1 minus P divided by n. Let us try to understand the central limit theorem for proportions. If x1, x2, etc. up to xn are counts from a Bernoulli trial with probability of success as p, that is expected value of x is p and variance of x is p times 1 minus p. What do I mean by that? Assume that x1, x2, etc. up to xn, these are counts from a Bernoulli trial. Let us take an example of returns by customers from an e-commerce portal. So, let us say n is the total number of purchases and let x1 be the number of returns. That means, the estimated proportion of returns is, that is P1 estimate. I am looking at from the first sample what proportion of them is returned. So, this will be x1 divided by n. Like this, we can calculate for all the remaining samples. We are going to assume that in the population, the proportion is P. We are forming a sampling distribution. From first sample, the estimated value is P1 hat, and from second sample, the estimated value will be P2 hat, which is x2 divided by n, and up to Pn hat, which will be xn divided by n. So, we are forming a sampling distribution where the values are P1 hat, P2 hat and so on up to Pn hat. So the sampling distribution of those proportions, the sampling distribution of these estimated proportions, that is P1 hat, P2 hat, etc. up to Pn hat, will follow a normal distribution where the mean is P and standard error is under root P times 1 minus P divided by N. Here N is the sample size. From this we can also derive that the statistic or variable P hat minus P divided by under root P times 1 minus P over N converges to a standard normal distribution. Let us discuss few examples in which the central limit theorem is used. Let me start with the first example. It is believed that college students in Bangalore spend on average 80 minutes a day texting on their mobile phones with a corresponding standard deviation of 25 minutes. Data from a sample of 100 students has been collected to calculate the amount of time spent texting. Now we need to calculate the probability that the average time spent by this sample of students will exceed 84 minutes. So what we have is the population mean mu, this is 80 minutes, and we also know the standard deviation of the population. Sigma, this is 25 minutes. The sample size, so basically the collected sample of 100 students. So the sample size N is 100. Now since we know the sample size, the sampling distribution of this sample will follow a normal distribution in which the mean is same as 80 and the standard deviation or the standard error of the sampling distribution will be sigma divided by under root n. So the standard error of the sampling distribution, this will be sigma divided by under root n, which is 25 divided by under root 100, so that will be 2.5. So we are looking at a sampling distribution which follows a normal distribution as per the central limit theorem. The mean of the sampling distribution mu is same as the population mean, which is 80, and the standard error of the sampling distribution is 2.5. Now we have to calculate what is the probability that the average time spent by the sample of 100 students will exceed 84. That is, we need to calculate what is the probability, the random variable x. So here when I say random variable, I am referring to the sampling distribution. This is greater than 84. Now remember, since the sampling distribution is a normal distribution, the value 84 minus 80 divided by 2.5, this will be a standard normal distribution. So basically what I have done is I have taken x minus mu divided by sigma divided by under root n. So this we know from the central limit theorem, this will follow a standard normal distribution. So this value is a standard normal distribution. So either I can calculate the probability directly from this particular equation, where we are looking at the probability x is greater than 84, where the mean is 80 and the standard deviation is 2.5, or I can convert that into a standard normal distribution and calculate the value. So when we take 84 minus 80 divided by 2.5, we will get 4 divided by 2.5, this is 1.6. So, we can now calculate what is the probability Z is greater than 1.6. So, using the norm dist function, we will get this probability as approximately 0.05. That means there is approximately 5% chance that a sample of 100 students, the average time they spend texting is 5%. If you notice the definition of central limit theorem, it says the central limit theorem is valid for large n. The question is, how large should be the sample size? Let me share an interesting story to convey why sample size is important. King Gustav III of Sweden, who lived between 1746 and 1792, was convinced that the coffee posed several health hazards and wanted to educate Swedes about the same. Coffee drinking was becoming popular in Sweden during 18th century despite a ban. King Gustav wanted to demonstrate the health hazards of coffee using an experiment. Luckily for him, a pair of identical twins convicted for a murder were scheduled for an execution at the same time. Gustav wanted to use them for his coffee experiment. Gustav commutated the death sentence to life imprisonment under the condition that one of them must drink 3 pots of coffee every day and the other 3 pots of tea. Gustav was convinced that they would fall sick and die quickly. He also appointed 2 doctors to monitor the health of the twins. In 1792, Gustav was assassinated and did not live to see the result of the experiment that he started. Both doctors he appointed to monitor the twins died few years later, and the twin who was drinking tea died at the age of 83. No one recorded the age at which the coffee drinker died. Well, the coffee was the winner. One of the major problems with this experiment was the sample size. It is very difficult to arrive at a statistical inference based on just 2 observations.